This is the Chapter 9 Proteins, Part 1 commentary. So I'm going to go ahead and do another quick review of intermolecular forces. Looking at this slide, slide 11, we have a list of various types of intermolecular forces. Now, we've touched upon what these intermolecular forces are from our organic chapters, and they're pretty much the same thing. I'm just going to go ahead and apply them to the side chain intermolecular forces that we find in proteins, such as in slide 12. It's these side chain intermolecular forces which help give the protein its overall shape and form. So, I'm going to go through each one of these very quickly. Let's go ahead and start from the very bottom. I do want to point out these are not ranked as far as strength of intermolecular force. They're just randomly listed here. I am going to start from the very bottom since that's the easiest to visualize, and I'm going to work my way upwards. So, electrostatic interactions. EI, electrostatic interactions. So, before I even get into this, the intermolecular force cohesiveness is driven by one major factor, and that is opposite charges attract. So the positive charge and the negative charge attract to each other. Now, we have different levels of opposite charge attraction. When we get really small, we have partial positive and partial negative, like we see in dipole-dipole and hydrogen bonding. But again, still opposite charge is attracting. So that makes up most of the intermolecular forces. Starting with electrostatic interactions, those are the most powerful opposite charges attraction. So the classic one was from our Chemistry 101, where you have a positive sodium and you have a negative chloride, and they're going to be attracted to each other, forming sodium chloride, opposite charges attraction. This is where we got the name salt. And that's when you have a positive and a negative, ions coming together, forming a neutral compound. And the common name for this is a salt. Now, we apply the same thing when it comes to electrostatic interactions. So in this case, I could have a carboxylic acid and a ammonia. And what happens is when we sit there and put it in water, water will sit there and react with a carboxylic acid. The hydrogen will come off and stick to the water, and it will then form a negatively charged, what we call a carboxylate. So notice we have a negative charge. If we have a ammonia in water on a different water molecule, the lone pair will actually bond with a hydrogen, and it will form a what we call a ammonium. But the take-home message is this: it will form a positive charge. So, if we have a strong negative charge, a strong positive charge, then opposite charges will be attracted. So, in this case, for electrostatic interactions, when it comes to a protein, you have your side chain intermolecular forces, and it's assumed that the protein is in water. So therefore, we have a negatively charged carboxylate side chain, and we have a positively charged ammonium from a amine side chain. Again, opposite charges attract. And we call this by several names. One name is a salt bridge, because it's opposite charges attraction between different parts of the polypeptide, aka protein, depending on how many amino acids it is. So opposite charge attraction, and then they're linked together like in a bridge. So this is a salt bridge. If it's a short distance away, I should specify if it's a short distance away, then it's a salt bridge. It is possible to have long-range attraction. So I could have, for example, on the N-terminus, for example, I could have a ammonium formed from an amine in water, and then you could have long-range electrostatic interactions. So short range is salt bridge, long range is, go figure, long range electrostatic interactions. In actuality, what happens is it's possible to have multiple attractions between side chains. So while this is occurring here, you could have this occurring over here. While a salt bridge is occurring between two side chains, you can also have a long-range electrostatic interaction, which is usually what happens. So many side chains spend their time mutually attracted to multiple side chains. So the next one has nothing to do with opposite charge attraction, and this is covalent bonds. In covalent bonds, we deal with covalent bonds all the time. So for example, this is methane, and this dash right here represents a covalent bond. This is when electrons are actually shared. Now, what happens is the nucleus of one atom and the nucleus of another atom, they're actually attracted to the electrons. And what they'll do is they'll actually share the electrons. They'll share it enough to complete the octet, but so they'll share it enough to complete the octet, but not enough to generate excess charge. So it's the best of both worlds. Covalent bonds are extremely strong. If you're curious, I'm not going to test you on this, but if you're curious on the ranking, for organic molecules, a covalent bond is stronger than a salt bridge in a polypeptide. So it's not enough to generate excess, and I know it's really messy, charge. So it says electrons are shared, complete octet, but not enough to generate the excess charge. So if I were to sit there and have a polypeptide, where you will see these form is due to cysteine bridges. So I'm drawing a crude side chain. So here we see two cysteines, CC, for cysteines. And what will happen is the hydrogens will come off they'll actually come off with a oxidizing agent, forming a brand new water molecule. Let's see. And then you'll have something. So when these leave, it'll just go ahead and create a covalent bond. These covalent bonds, again, are as strong as any of the covalent bonds that you'd find in the backbone that make up the amino acid polymer. So these are the strongest when it comes to the side chain intermolecular forces, and then it's followed by the strongest to least opposite charge intermolecular forces, such as salt bridges, long-range electrostatic interactions, and then the others, dipole-dipole hydrogen bonding. So this is the only one we're going to touch upon in this course, and when you have this right here, again, it's a bridge between these two side chains, so we have different names for these. We have a cysteine bridge. The other name for this is, because it involves two sulfurs, a disulfide bridge. Yes, in biochemistry, just like organic, we have more than one name for the same thing. All right. So in this case right here, let's go to the next one. London force and hydrophobic interactions. That pen doesn't work right. Okay. Let me practice with my pen really quick. All right. So the two forces are actually really related. So I could sit there and have again, polypeptide, and I could have a side chain which has nonpolar, which is a nonpolar side chain. So for example, I could have two leucines. So this is London forces. I'm not going to go into detail about what London forces is. Please review your original intermolecular forces at the beginning, video commentary at the beginning of the course when we talked about intermolecular forces, London forces. But bottom line, this is London forces. Notice the London force side chains are nonpolar. So the nonpolar side chains are going to want to be attracted to each other. Now, at the same time that London forces is occurring, because it's nonpolar, you also have hydrophobic interactions. And this is where you have water molecules. Water molecules are going to be polar. And it turns out that water molecules want to avoid the nonpolar side chains, so much so that they'll actually start pushing and nudging the polypeptide such that it forces so that the water forces the nonpolar forces the nonpolar side chains away from the water toward the center of the polypeptide. So this is an indirect cohesive force. They are attracted to each other, so that is cohesive when it comes to London force. But alternately, indirectly, the water molecules are actually also continuously pushing the polypeptide together. And it wants to do that to escape the nonpolar forces. When a polypeptide is first created and it has these nonpolar side chains, water will instinctively start pushing immediately on the polypeptide in order to escape interaction of the nonpolar forces. So here's my polypeptide afterwards. Notice how it's scrunched together due to water pushing it together in order to escape interaction of the London forces. So during this actual occurrence, we call this hydrophobic packing, because it's water that's actually pushing it and packing it together. So London forces and hydrophobic interaction, these are interchangeable. You could sit there and put either one of them as the correct answer if I were to ask you about the intermolecular force when it comes to leucines. Let's go to the next one. Now we have dipole-dipole and hydrogen bond. So let's stick with the easy ones first. Dipole-dipole forces. It occurs between two molecules, or in our focus, side chains, which have individual dipoles. So just to give you an example, I could have something like this. This is hydrogen disulfide. It turns out that sulfur is more electronegative than hydrogen. Consequently, you're going to have an overall dipole that comes up. Now, with this overall dipole, on one side you have an overall partial positive, and near the arrow it's actually an overall partial negative, and at the tail you have a partial positive. So partial negative, partial positive. So basically you have opposite charge attraction. Really this should be upside down, but opposite charge attraction between the overall dipole, partial positive, partial negative. If we were to sit there and apply it into our side chain intermolecular forces, here we have two cysteine. Note they're not covalently bonded together, and it turns out each one individually has a overall dipole. So we have dipole-dipole forces. Now, hydrogen bonding. People often confuse dipole-dipole and hydrogen bonding. So, here are the requirements. Both molecules or side chains I know it's getting really messy. Both molecules or side chains, if you apply it to polypeptides, require a overall dipole they require a nitrogen, oxygen, or fluorine. And one molecule needs a lone pair on a nitrogen, oxygen, or fluorine. The other molecule needs a hydrogen, which is directly covalently bonded to a nitrogen, oxygen, or fluorine. Just to use organic molecules, if I were to have something like this, this is a pure substance. So in this instance, we see hydrogen bonding occurring between like molecules. And what's going to happen is, if there's a lone pair present on a nitrogen, oxygen, or fluorine, and provided these both have dipoles, by the way, so the first one is achieved. They both have a nitrogen, oxygen, or fluorine. One of them has a lone pair. The other one has a hydrogen, which is directly covalent bonded to a nitrogen, oxygen, or fluorine. So therefore, you have hydrogen bonding that can occur. Basically, a hydrogen bonding is a super powerful dipole-dipole force. It turns out nitrogen, oxygen, and fluorine are so electronegative that they create a extra super powerful partial negative and partial positive on its overall dipole. This allows the hydrogen to get extremely close, almost to the point of being ripped off from its original covalently bonded molecule. And it allows for this extreme opposite charge attraction. Now I just wrote general overall dipoles just so you could see them, but in reality it's the hydrogen itself which is going to have the, let me just erase part of that. So in reality, it's the lone pair which is going to have the really powerful partial negative, the hydrogen which can have a really powerful partial positive, and then opposite charges attract. So think of it as a super powerful dipole-dipole where the hydrogen and lone pair have a extreme opposite charge attraction. And if you study the energy related in this hydrogen bond, it's actually enormous and it's very powerful. It's a very powerful bond. So there are physical chemists who study this all day and it makes their day. So the next question is, if one atom, or I'm sorry, if one molecule or side chain does not what's the word I'm looking for? Does not meet the criteria, then basically the intermolecular force is downgraded to a dipole-dipole. So it's automatically a dipole-dipole. So let's go ahead and play with this really quick. Let me erase this. I could have a situation where one of the molecules achieves the criteria. So for example, here I have a water molecule, and then I have a hydrogen sulfide. This one right here has a lone pair or a hydrogen covalently bonded, so it's ready to hydrogen bond. This one, however, is not. Although it has an overall dipole, it doesn't have a nitrogen oxygen or fluorine. So the best it could do is dipole-dipole intermolecular forces. So if one of them doesn't meet the criteria, it's automatically downgraded to the next potent intermolecular force, in this case, dipole-dipole. So nature settles for the next potent one. So I could have a situation like this right here. Here I have a carboxylate ion. Here I have a cysteine. So here we have a aspartic acid D. Here you have a cysteine. Here we have a amine. Or amine from a lysine. Okay. And then here I have a serine. So in green, if I wanted to demonstrate a dipole-dipole intermolecular force, this would be dipole-dipole. Although the serine is a potential candidate for hydrogen bonding, the cysteine is not. So this would be dipole-dipole. Technically, aspartic acid and lysine, they have dipoles. So even though they would like to form, if given the opportunity, they'd like to form a salt bridge or long-range electrostatic interactions. If they're near a cysteine, then what they'll do is they'll also do a dipole-dipole intermolecular force between each other. So same thing with this one right here. Now when it comes to hydrogen bonding, and I'll just go ahead and use a blue. In this case, we have a lone pair on a nitrogen oxygen or fluorine. And I would need a hydrogen directly attached to a nitrogen oxygen or fluorine. So in this case, between the lysine and the serine, you would have hydrogen bonding. Notice there's a hydrogen directly attached to a nitrogen oxygen or fluorine on serine. So if I wanted to, I could have this hydrogen and then this lone pair also hydrogen bond. So it's possible to have multiple intermolecular forces, and provided it meets the criteria, you could have hydrogen bonding. So that concludes